Hi. So here we are. The data set is given in the column wise where subdivision and age, and these are the basically uh, the month wise rainfall which has happened in and then basically annual is nothing but the cumulative from Jan to December. Same way quarterly is sum of the quarter rainfall. So to start with the project, first we need to do the data exploration, how the data is, keeping in mind what we are going to do and whether it is good for us or not, and what are the changes we need to do in the data set in order to make it compatible with our model. And the model which I have used is the seasonal ARIMA model to find out to do the prediction, and then also done the model assessment. So initial analysis shows the data set has a lot of data which are missing. Basically, there is a gap in the data. It's not continuous data. And also we can infer from the data is that in India, the basically June, July, August, September, these are the 4 months which has heavily rain because those in the data set we see that there are no zeros in those months. Whereas in December, November, January, February, uh, and March, we have a more number of zeros. So these months are dry months. So basically there is no rain in months. And more in the, so this is the analysis which can make just by seeing the data. And we can see how the rolling mean and rolling standard deviation is going over the whole data set. Also, now as we infer from the zero analysis and also this data when we plot in a graphical manner, then we see that so the basically here the purple one, which is July, then again June. So these are the basically then after that we have brown one. So this if we here June, July, August, September. These are the 4 months which has the data the rain volume is going to basically, and the y-axis which I have taken is I have divided by 10 to reduce the number of scale. Um, and basically, if you will now here the 38 divisions, 36 divisions, and how the rain is happening in each month over 115 years. So it's clearly we can see that the maximum rain happens in the coastal Karnataka and the Kerala and then in Sikkim. So these are the initial inference we can make from the data set. Now, in order to proceed further, I have done the seasonal decomposition of the data set, and we found that how the data is observed, how the trend is happening, what is the seasonal components, what is the residual. And basically, this is done on the different kind of data sets. First, I had to choose the whole data set and then see how it is. Then we took the logarithmic data, training data set, and then you see that how it is happening. So both are, the seasonality is remaining almost the same, but other things like residual is changing, observed value is same, trend is almost similar. So here we can say that it looks like there is no the pattern in the seasonal component of the data set. So to make sure whether there is a seasonality in our data set or not, I have used the autocorrelation function where we can see that the autocorrelation function is constant. It's not changing. So it means that there is not much seasonality in our data. And so using this, we have found the P and Q basically for our ARIMA model, which seems to be, and this P and Q doesn't, there are different diagrams here. So one is based on the whole data set, another is the training data set, another is on logarithmic training data set. So in all the data set, we see the P and Q is almost same. P is equal to 2 and Q equal to 3. So now using this P and Q and the 12 months of duration, we find we plot our Harima model and see that for the last 80-20 basically in the 20 how the the test data performs against the training data. So using the 80 models I have used as a training and then 20 as testing. So the red line here it shows the value which is predicted by our model. And using this value and finding out based on the actual value, the root mean square error comes out to be 11.92, which seems to be a pretty good model. So basically, there are some differences here because obviously the data is not continuous. Some of the years are dropped. So because this is a supervised learning, so supervised learning models is completely dependent on the data accuracy. Bad data, bad model, bad prediction. So so there are some kinds of noises there, but then that is the max which I could get. And first, then as I talked about the seasonality through the autocorrelation function, and then also the use the decay Fuller test to find out what is this, whether the data is stationary or not. So initial data doesn't seems to be stationary, but the logarithmic data shows pretty stationary results. So I use the logarithmic value of the initial dataset value. I'm using that. Thus, this model is um, built using those logarithmic trend data. Also, using the same training data, I have used profit model to predict how the 5 years of the rain from 2015 to 2020. Using this model, if you see the what is the performance, the cross validation and performance matrix, then I'm getting RMSE of 108, which is lower than the our ARIMA model. So I feel that the ARIMA model is better uh, here, where the seasonality and the stationary are more important. So right now this is built using on the Jupyter and with Python 3.7 in a static environment. Obviously, this can be automated by using some REST services call, which say pass the parameter of the division, and the model can give the result as the output JSON back to the as a response to the JSON call. Using this, basically, ARIMA model, we can see that we're not 100% matching, but it is good giving results. We can find out what is the rain going, which is going to happen on the line 10 years, and or tomorrow, or day after tomorrow, and accordingly next quarter, and we can do the commodity trading based on that. Uh, that's all. That's all from my side. Thank you.